Picture this, a single gold bar, small enough to hold in two hands, worth more than $1 million. Humanity has fought wars, crossed oceans, and built empires chasing this metal. But where does it actually come from? Not from magic or rivers of nuggets like in the old days. 90% of today's gold is locked inside ordinary-looking rock, buried miles underground, in amounts so tiny you'd never see them with the naked eye. To produce just one simple gold wedding ring, miners have to blast, crush, and chemically process over 3 tons of rock. That's insane. Welcome to Factory Raw, the channel that takes you inside the world's most incredible industrial processes. Today, we're pulling back the curtain on modern large-scale gold production. From raw ore deep in the earth to pure, certified gold bars ready for vaults, jewelry, or circuit boards. We'll go step by step through every stage: mining, crushing, grinding, concentration, extraction, recovery, smelting, refining, and final casting. This is heavy industry at its most extreme. Massive machines, dangerous chemistry, and cutting-edge technology. Let's dive in. The journey starts at the gold deposit. Gold is almost never found pure in large quantities anymore. In modern mines, it's microscopic particles scattered through hard rock ore, often just 1 to 10 grams of gold per ton of rock. That's like finding a needle in a swimming pool. There are 2 main types of mines. Open pit mines, huge terraced craters, some over 1 kilometer deep and several kilometers wide, like the Super Pit in Australia or mines in Nevada. Underground mines, deep shafts and tunnels for richer or deeper deposits, like South Africa's Mponeng mine, the deepest in the world at over 4 kilometers. Geologists first drill core samples to map the ore body. Once confirmed, the rock is blasted with carefully placed explosives, sometimes thousands of tons at once. Giant electric shovels scoop the broken ore into haul trucks that can carry 300 to 400 tons per load. These monsters run 24/7, moving millions of tons of material every year. The ore is transported to the processing plant, while waste rock is dumped in designated areas. At this point, it's just low-grade rocky material containing gold, silver, copper, and other minerals. Arriving at the mill, the ore is still in large chunks, some the size of microwaves. Primary crushing, fed into huge jaw or gyratory crushers that squeeze the rock until it breaks into pieces smaller than 15 to 20 centimeters. Secondary and tertiary crushing, cone or impact crushers reduce it further to sand-sized particles. Then comes grinding, the most energy-intensive step. The ore goes into semi-autogenous grinding, SAG, mills. Enormous rotating drums up to 12 meters in diameter, lined with steel and partially filled with the ore itself plus steel balls. Water is added to make a slurry, and as the mill spins for hours, the rock is pulverized to particles finer than 100 microns, about the thickness of a human hair. This fine grinding is crucial. It liberates the tiny gold grains trapped inside quartz or sulfide minerals. A single large mill can process 100,000 tons of ore per day. Before chemical extraction, modern operations add an intelligent sorting step using the crushed material. As the ground ore travels on conveyor belts, high-tech sensors scan every piece. X-ray fluorescence detects metal content. Near-infrared spectroscopy identifies mineral types. 3D laser scanning measures density. Computer systems analyze thousands of particles per second. Pneumatic ejectors blast waste material off the belt at speeds up to 5 meters per second. You can hear the rapid-fire whoosh, whoosh, whoosh. This pre-concentration can reject 20 to 50% of barren waste before it even enters the chemical processing stages, saving massive amounts of energy, water, and processing chemicals. Some facilities use additional gravity separation with microwave or electromagnetic sensors. It's like having an intelligent filter that only lets valuable ore through to the expensive extraction stages. Now, the ore goes through concentration to further enrich the gold content and reduce processing costs. The most common method is flotation. Chemicals called collectors make gold-bearing sulfide minerals hydrophobic, so they attach to air bubbles. Frothers create stable foam, and the gold-rich froth is skimmed off the top. Gravity methods like shaking tables or Nelson concentrators separate heavier gold particles using centrifugal force, spinning at high speed to push dense gold to the outside, while lighter waste stays in the center. The result? A concentrate 10 to 50 times richer in gold, with 80 to 90% of the waste rock removed. What started as tons of low-grade ore is now a much smaller volume of high-grade concentrate ready for chemical extraction. Here's where things get really industrial, and this is a step many people never hear about. About 20 to 30% of the world's gold is locked in what's called refractory ore. The gold is imprisoned inside sulfide minerals like pyrite or arsenopyrite. These minerals form a protective shell that blocks cyanide from reaching the gold. It's like the gold is in a microscopic vault. You can't just leach this ore. You need to break the vault first. There are 3 high-tech methods. Roasting, the traditional method. Concentrate is fed into massive rotary kilns or fluidized bed roasters at 500 to 700 degrees Celsius. Oxygen burns off the sulfur and arsenic, turning solid sulfides into porous metal oxides and releasing sulfur dioxide gas. The roaster is a beast. Imagine a rotating drum 50 meters long, glowing red hot inside, processing hundreds of tons per day. The sulfur dioxide is captured by scrubbers and converted to sulfuric acid as a byproduct. What comes out is called calcine, a crumbly, oxidized material where the gold is now exposed and ready for cyanide leaching. Pressure oxidation, the modern solution. Concentrate is cooked in giant autoclaves. Think pressure cookers the size of buildings, at 200 to 225 degrees Celsius and 30 to 35 bar pressure with pure oxygen. Under these extreme conditions, sulfides oxidize in hours instead of requiring high-temperature roasting. The gold is liberated without atmospheric emissions. These autoclaves are engineering marvels, titanium-lined vessels 4 to 5 meters in diameter, with walls 15 centimeters thick to handle the pressure. They process slurry continuously, and the whole system is monitored by computers managing temperature, pressure, and chemistry second by second. Bio-oxidation, nature's way. Some operations use bacteria, specially cultivated thermophilic microorganisms, that literally eat the sulfide minerals over 4 to 7 days in warm, aerated tanks. These bacteria colonies oxidize the sulfides at room temperature, releasing the gold without heat or high pressure. It's slower but cleaner and uses less energy. You're essentially farming billions of microscopic gold miners. After any of these processes, the oxidized material goes forward to cyanide leaching with 90 to 95% of the gold now accessible. Without this step, refractory ores would be economically worthless. The core extraction step, cyanide leaching. The finely ground slurry is mixed with a dilute sodium cyanide solution, 0.01 to 0.05% concentration, weaker than some household cleaners, in large tanks. Air or oxygen is added, and agitators keep everything moving for 24 to 72 hours. The chemical reaction. Gold dissolves as a soluble complex, AuCN2-. This process, called cyanidation, recovers 90 to 97% of the gold in many ores. For low-grade ores, heap leaching is used. Ore piled in huge heaps and sprinkled with cyanide solution. Safety note: modern plants recycle 95 to 99% of cyanide, detoxify tailings, and monitor constantly. Cyanide breaks down quickly in sunlight and is strictly regulated. The gold-rich, pregnant solution goes to recovery. Carbon in pulp, CIP, or carbon in leach, CIL. Activated carbon adsorbs the gold complex like a sponge. Loaded carbon is stripped with hot caustic cyanide solution in elution columns. Then, electrowinning. Electric current forces gold to deposit as a brown sludge on steel wool cathodes. The sludge is filtered, dried, and ready for smelting. In a furnace at 1,200 to 1,300 degrees Celsius, the sludge is melted with fluxes, borax, silica, soda ash. Impurities form slag that's skimmed off. The molten metal, now door, is poured into molds. Door bars are typically 70 to 90% gold, 10 to 30% silver, with traces of copper or platinum group metals. At specialized refineries, Miller process, most common, chlorine gas bubbled through molten door removes silver and base metals as chlorides, yielding 99.5 to 99.8% gold. Woolwill electrolytic process for ultra purity. Gold anode dissolves in hydrochloric acid with gold chloride electrolyte. Pure gold plates onto a cathode, achieving 99.99% or 4 nines purity. Some refineries use aqua regia or other solvent extraction methods. Gold mining isn't just about gold. Door bars contain significant silver, which is recovered during refining. In the Miller process, silver chloride is converted back to metallic silver. Electrolytic refining can also produce pure silver cathodes. Many mines also extract copper, zinc, or platinum group metals as valuable byproducts, making operations more economical and reducing waste. Pure gold is remelted in induction furnaces under vacuum or inert gas to prevent oxidation. It's cast into bars, large 400-ounce, 12.4 kilograms, London Good Delivery bars or smaller 1-kilogram bars. Each bar is weighed to the milligram, stamped with serial number, refiner hallmark, purity, 999.9, and year. Multiple assays, fire assay, X-ray fluorescence, confirm purity. Bars are sealed in tamper-evident packaging and stored in high-security vaults. But the journey doesn't end at the vault. Each bar must be carefully packaged for transport. Gold bars are wrapped in protective film, placed in sealed, tamper-evident bags with unique serial numbers matching the bar. Multiple bars are packed in secure wooden crates with foam padding, then steel-banded and sealed with security tags. Storage happens in specialized facilities, central bank vaults with meter-thick concrete walls, multiple vault doors, biometric access, 24/7 armed guards, and surveillance systems monitoring every angle. Delivery to market uses armored vehicles with GPS tracking, escort vehicles, and insurance coverage worth millions. Bars travel from refineries to bullion dealers, central banks, or directly to manufacturers making jewelry and electronics. Factory safety is paramount. Workers undergo extensive training. Facilities have emergency shutdown systems, strict protocols for handling chemicals and molten metals, air filtration systems, and regular safety audits. Modern gold refineries are some of the safest industrial facilities in the world. That's the complete journey of gold, from microscopic specks in raw ore to certified pure bars, using some of the biggest machines and smartest chemistry on the planet. Modern gold production is far safer and cleaner than in the past, with many mines focusing on water recycling, land rehabilitation, and community support. Thank you for watching Factory Raw. If this blew your mind, smash that like button, subscribe, and turn on notifications. We've got more raw industrial processes coming. See you in the next one.